to NURFM.com, a broadcast service of the University of Newcastle.
It's 21 to 12. We're joined now by the University of Newcastle's Professor John O'Connor, and an interesting topic today. I like this one. We're taking a look at some X-rays, but they're a different kind of X-ray. They're on quite a large scale, John, aren't they?
Yes, well, technically they're muon rays, but not X-rays. But yes, the question, and people are familiar with X-rays and the fact that we get X-rayed all the time to see what's happening inside us. But the question is, how would you X-ray a mountain? And why would you X-ray a mountain? Well, certainly if you've got a mountain that is potentially an active volcano, you want to know what's going on underneath. And it's a bit of a challenge. You don't want to go drilling holes in that because, bang, you might actually create a volcano in the process. And you also want plenty of warning. So there's a project which has been underway, which first arose many years back by a physicist who wanted to try and find the hidden chambers in one of the pyramids. And he put detectors inside the pyramid and effectively X-rayed the pyramid. Now,
did it work for him?
They thought there were secret hidden chambers there, and they found none. So it doesn't. Well, it worked in the sense that they didn't find any, but that doesn't mean that. Well, presumably means there aren't any there to find. But muons, how do you produce the muons? I mean, with an X-ray machine, we know you fire up the machine and produce X-rays, but we have this benefit. They're all around us. We're constantly bombarded from space by high-energy particles. They collide with the oxygen atoms and the nitrogen atoms, and they produce a shower of these things called muons. And they travel quite a distance. In fact, they travel much further than X-rays. They'll travel through a kilometre of rock or more, and they head in all directions. It's not just going straight down. And so if on one side of the mountain you put a detector which is looking at what's coming through the mountain, and you pick up these muons, you can detect where the higher density and the lower densities are, and you can monitor that with time. It's fairly inexpensive equipment. On the scale of things, it's a few $1,000s, but they're being made much more compact. And in fact, the reason they're being made more compact is because we've built things like the Large Hadron Collider, where they want to put a lot of detectors in one space. And so the combination of that development and the mass production means they've come down in size. Unfortunately, you can't control the rate of muon production, so you've got to rely on what's happening naturally, so it can take a while. But these can be set up as a continual monitoring process beside a mountain, and over time build up a very clear picture of what's happening, and then see very subtle changes in it. And they've already done this for a number of situations. In fact, I'll show you this picture here, which is the top picture is a picture of the mountain as you take a photograph of it, and then there's a colour enhanced image that shows you how the density is changing within the mountain, and there are some areas which are bright red and some areas which are blue, and these all relate to the density of rocks, and that allows you to identify where the hot spots are in the mountain or where the active areas are, and the thing you'd be looking for would be changes over time.
So it works well with the volcanoes when they do that?
Well, certainly at present they can look through a couple of kilometres of rock, which is about the size, what you see around the base of a volcano. They've identified some features. The particular diagram I just showed you, they're able to go back and then with gravimetric readings actually prove that what is there is real. So yes, they can make those measurements as well. So yes, it works. They've looked at a number. In fact, the Japanese really got this underway. They initially looked at Mount Tsukuba in Japan, and then a couple of others, and now they're doing the same thing in France and in South America. So this is starting to expand. But it gives you another way of looking at rocks, because normally what you try to do is hope there are earthquakes or set off explosions and look at the seismic waves that travel through, but they don't always give you the information.
Can it be utilised in mining in any way? Would that be something that would be beneficial for them?
Certainly it could be utilised in mining, but the trouble is, on the side of a mountain you could. Either that or you've got to dig a deep hole down and sit there and watch what comes down from space. But yes, certainly you could do it that way. You could look at the profile of a mountain through this process and identify what's there already, and maybe identify what, especially if there's a change. This is particularly good for changes because you can see things happening with time. With the profile as it is, you've got to do a lot of interpretation, and other information would help. But for instance, if there's a gold-bearing ore in the middle of that thing, it would probably show up as a very good absorber. but it could also be a lead bearing or so.
Yeah.
You need a bit more information.
Okay, well that is great. Great topic today as always. Thank you for that, John.
Thanks, Dave.
Joining us from the University of Newcastle, Professor John O'Connor, back in a couple of weeks' time.